Okay, this is an overview of the BGBTech Game Engine. This green area here represents the actual 3D part of the 3D engine, or the main game engine part. The architecture is largely divided into three major areas, one of which is the renderer, the second of which is the server, and in the middle is an area known as common. The renderer mostly does 3D rendering and other similar tasks. This would be all the stuff that is generally visible on the screen. This would also include user input handling such as mouse and keyboard. The server end, on the other hand, primarily manages things like the entities and game logic. This would also include things like physics. Common represents an area shared between the client and the server. This area largely manages things like the scene graph and also to some extent message passing between the client and the server. Common also generally contains most of the voxel code within the present form of the engine. The yellow area represents a lot of the VM and backend code. The garbage collector is a concurrent mark sweep garbage collector. This is the assembler and linker. It takes ASM code and assembles it into native code at runtime. This native code is then linked against the running program image. This part here is the scripting VM. It takes script code at runtime and compiles it into bytecode. It may then compile this bytecode into threaded code, which it may then execute. This here is the metadata tool. Its main task is parsing C headers and generating metadata. This metadata may then be stored in the DLLs or exe files using a WAD-based container format. Additionally, it may also store bytecode or resource data. This here part represents the dynamic type system in object-oriented facilities. Additionally, it contains the virtual file system. It also serves as a major hub for much of the rest of the 3D engine. It also makes use of metadata for sake of generating glue code to interface with native code. The 3D engine is Quake-like in many ways. It has many similar types of entities as well as similar game logic. It uses a voxel-based terrain system similar to that in Minecraft. Chunks are 16 by 16 by 16 and are organized into regions of 32 by 32 by 8. It is also capable of using brush geometry as well as visor patches and meshes. It uses real-time lighting and stencil shadows. The shadows are based on depth pass. It uses a Quake-inspired lighting model, but adds on some Doom 3-like elements, box lighting and optional fall-off and projection textures, as well as hybridizing it with Phong lighting. It also supports normal parallax and luma mapping. Most models use a variant of the AC3D model format. The format is extended to support skeletons and animations. It also handles textures slightly differently, in that it uses shader names rather than relative image paths. Voxels. They have a 12-bit type, 4-bit block mode, around 24 bits of auxiliary data, an 8-bit delay, and 16 bits for light data. This currently adds up to about 64 bits per voxel. Future expansion, if needed, may involve escape blocks, which would encode an index to an object representing expanded block contents. Note that block type numbers are assigned statically from the bottom up and dynamically from the top down. BGB script. It is based mostly on ECMA script, which includes JavaScript and ActionScript. Additionally, it is influenced by Java, C#, C, Scheme, and Self. However, it retains a relatively conventional language syntax. It supports both static and dynamic types. It supports both prototype and class instance object-oriented features. It supports both ActionScript style and Java C# style declaration syntax. Extensions support most of the C-type system, in other words, structs and pointers. It supports direct calling between BGB script and C code. This does not require writing glue boilerplate. It can, with tool assistance, allow direct calls from C code into BGB script. Native import allows importing native libraries. This depends on metadata gained via header parsing. Native package allows declaring code for export to C. This is similar to extern C in C++. BGB script VM. It is based on compiling script code into bytecode. This may be executed directly or saved into object files for later use. The VM bytecode is stack-based, like the Java VM or CLR bytecode. It often uses prefixes to identify types, but fixed type opcodes also exist. The absence of a type prefix indicates dynamic type. The bytecode is not executed directly, but is typically converted into threaded code. This has nothing to do with multi-threading. Threaded code is an execution method where the code consists entirely of function calls, say into C functions, which implement the logic. While still slower than native code, this is capable of greater performance than a naive while loop and switch interpreter without necessarily being significantly more complicated. Although most of the VM logic is written in C, some parts are accelerated via dynamically generated ASM/native code, and some other parts depend on this in order to work.